Hello, am I audible? Hello, am I audible? Ramamani, can you hear me? Okay, thank you. So is my screen visible? Screen sharing. Okay, so now today I will start the problem solving session for the physics to computational thinking. This is the fourth class. So here today I will show some uh, codes for Mathematica to solve the differential equation and plot them, and then I will show some code for integration, and then I'll show the code for uh, the Euler method to solve differential equation numerically but using mathematics. So first is the using the desolve, that is I have shown multiple times, but still again I am showing it because physics is mostly consist of differential equation, so we need to solve them. So this is the um, solution for the differential x double dash t equal to minus xt, where the initial condition x dash first derivative of x t at 0 is equal to a. So we get the solution xt equal to c1 cos t plus a sin t. Now I will give another initial condition, that is x0 equal to b. So now you can see that the c1 is changed with b, so b cos t plus a sin t. Now if I change the initial value t equal to 0 to t equal to 1, then we get this kind of complicated solution, that is b cos t a sec 1 sin t plus b sin t tan 1. So now for differential equation, now what we'll do is I'll show some how to do the differentiation in mathematical. So this is differentiation of x square sorry. So this is differentiation of x square of first derivative, so this is 2x. Now I'll give another little complicated. So this is the function x square plus log x, the differentiation is 1 by x plus 2x. Now if I put log x square, then it is 2 by x plus 2x. This is the third derivative of the function x square plus log x, which is 2 by x cube. Now I'll just plot it. This is the plot. Now if we put n here, then we get the nth derivative, which is x to the power 2 minus n factorial power 2n and so on. Now again take a derivative of a little complicated function, that is exponential of x square exponential of x square plus log x. The second derivative is 2 e to the power x square minus 1 by x square plus 4 e x square x square. If I plot this, I get this kind of plot. Now just change the range to minus 1 1. This is the plot in the range minus 1 to 1. So this is the blue line represents the function exponential x square plus log x, and this is the second derivative of it. So here you can see the blue line represents the function, then the yellow line represents the first derivative, and the green line represents the second derivative. Now using the solve function, x to the power 2 plus log x 2. X. So here the first thing is the derivative. We are taking the derivative of this function x square and x square plus log x. We are taking the second derivative of it, and then that equation is equal to 0. Then we are solving it for x. So we are getting two roots, that is x equal to 1 by minus 1 by root 2 and x equal to 1 by root 2. Now we will just now here I have assigned that solution to the value s. Now s1 gives us the first root, and then s2 gives us the second root. Now let's see some complicated example of t and use of this function d, that is sine x to the power 9 plus cos x to the power 8. X comma 7. So this is the function sine x to the power 9 plus cos x to the power 8. The seventh derivative with respect to x is given by this. This is a big number or expression. Then again we can have the nth derivative, this cos of x and cos n pi by 2 plus x. So if we replace this with sine n pi by 2 plus x, now if we change the function to sine x to cos x, sine x multiplied by cos x, we get this kind of solution. Now also we can do the derivative with respect to two variables like sine x y by x square plus y square comma x comma y. So this is the derivative of sine xy by x square plus y square. This t function can also be used to get the derivative of a symbolic function f. So like if I write x f of x multiplied by f dash x. Here you can see that this is giving the derivative of fx f dash x as fx f dash x plus x f dash x whole square plus x fx x f double dash x. Again we can do the partial derivative of a function, that we can get using this escape pattern, which will give you this 3 dot, then you have to write pd, which will give this thing partial d, then again the escape. Yeah. So this online version does not get this delta. I don't know how to write the subscript in this online version. Now let's define a function f x dash x cube plus 3 x square minus 3 x minus 1. Okay, so now plot of f x comma x minus 4 to 2. So this is the plot of the function x cube plus 3x square minus 3x minus 1. Solve t of f of x comma x equal to 0 comma x equal to minus 1 minus root 2 x minus. So this is the turning point of the function, that is the minus 2.414 is somewhere here, and 0.414, that is somewhere here. This is the turning point of this curve. Okay, so now this is the application of d operator. Now we'll go to the integrate function. It is integrate e power n comma x. This is the integration of x to the power n, that is x to the power 1 plus n by 1 plus n. So now here this is, I am going to manipulate the value n from -10 to 10, plot this function. Here you can see that the plot graph is changing. So basically integration is finding the area under the curve. So now if I plot a curve x from 0 to 1 using axis. So basically if I integrate this function 1 by x cube plus 1, then it will give me the area under this curve. So now integrate so this is the value of this area 1 by 18 multiplied by 2 root 3 pi plus log 64. So this is the value. Now again we can use this escape button to insert this integration sign. Now here square root of x plus square root of x escape dd x. So here we are integrating this is the usual writing notation when we write it in notebook, that integration of the function square root of x plus square root x dx. So this is the integration of it. This can be also written in. So these are the two equivalent way to write the integration. So now if there is a problem like integrate pi sin x whole square x 0. So this is the value of integrating pi sin x square whole square. So from x 0 to pi. So this is basically a problem where the question is to compute the volume enclosed when y equal to sin square x for pi by 2 for in the range of x pi by 2 to pi. So basically this particular thing sin x square, this is the curve which is rotating along the x axis. So now we'll visualize the thing actually. So revolution plot 3D sin x whole square x comma 0 comma pi revolution axis x. So basically this is the volume that is measured by this particular formula integrate pi sin x square. So the curve is sin x square. Okay, now we are measuring the volume that is covered by this particular curve when it is rotated around with respect to the axis x. Now if we change the range, we can see two lobes. So basically this is a, if you check this upper line, that will actually corresponds to the sine curve. So basically one sine curve is rotated around the x-axis. Now if we put cos here, that will change it to the cosine curve. So here you can see that it is starting from the point 1 and so on. Now again we will show another plot. Integrate 2 pi x and so on to so this is a problem where find the volume enclosed when y equal to x into x minus 1 whole square, and in the range for x 0 to 1 is rotated about the y-axis. So now again we will load this. So revolution plot 3D x minus 1 So evolution plot 3D 0. So this is the volume uh, that is calculated here by pi by 15. So this is the uh, plot of this particular curve, where this this plane denotes the this plane is denoted actually added to the plot by using this particular line, revolution plot 3 is 0. Now if we remove this particular line, revolution plot 3 is 0, we will see this kind of uh, graph, this kind of revolution plot 3D. Now again there is a problem that is a bit lengthy. First we need to define two functions, fx equal to x and pxs equal to x square. So this is the two function. Now the let's me first tell the problem. Find the volume of the region formed by rotating the area between fx equal to x and gx equal to x square about y-axis. Okay, so basically these are the two functions. So by so the region between, first we need to find the region between them, and then we have to find the area of the area volume by rotating that particular region. So first we need to find the region, and so to find the region we need to find where these two curves actually intersect each other. Fx dx. So these two functions actually intersect each other at 0 and 1. Now plot gx fx x 0, 1, 15. Okay, so this is the area between these two curves fx and gx. So the straight line denotes to the fx, and gx is the blue line is the x square. So between these two curves, this is the area. Now what we'll do, we'll see the evolution. Revolution plot 3D. X fx x gx x0 to 1 dot style per second 0.6. Here you can see that two plots has been done simultaneously. If you can see closely, you can see that this is for the fx equal to x, and this curved surface is for the gx. Now what we will do, we will get the value, that is integrate by x fx minus gx (0 to 1). This is a pi by 6. So this is the volume between these two curves, that is pi by 6. Now again go back to simple integrate, where we will integrate with a multivariable function. So for x plus x star y, integrate x plus x star y comma x. Here this function is the two variables is x and y, but here this is only integrated with respect to s. That's why we get the answer as x square by 2 plus x square y by 2. So here I am just doing the 3 plot of this function and then manipulating it with respect to the range of the axis, x from minus a to a, y from minus b to b, and the range of a is minus 10 to 10, b of also minus 10 to 10. Now what I will do is I will copy the same function and plot, do the integration with respect to both the variables. Now we will get x square y plus x by 2 plus x square y square by 4. So now again do the same thing. Now I can see that doing the integration with respect to one variable and with respect to another two variable is how much difference is there. Okay, so now again integrate 1 by square root of 1 plus x square square root of 1 plus x square. Okay. Yeah, so this is the integration of 1 by square root of 1 plus x square. So now I'm doing this one is uh, only integration, but here it is I'm giving a range of x from 0 to 1, so this is the answer. Now what I will do numerical integration. N integrate N integrate y square root of 1 plus x whole square x 0 to 1. So this is the answer 0.881374. So numerical integrate is used when the integration of a function is not very easy. Only then this numerical integrate is used. So get the value of the integration at each point. And integrate I square root of 1 plus a plus x square x 0, 1. So this is a function that is having the parameter a, and the function is actually a numerical integration of this particular function 1 by square root of 1 plus a plus x square, with the range of x is, the integral limit is 0 to 1. Now we'll plot this function. Plot of f a with a 0 to 100. So this is the plot of the function. So numerical integration can also be assigned to a function. Now again we'll return to the solve, where we'll solve coupled differential of the equation. So d solve equal to d solve. Anyone have any question?
No, sir.
Okay. Okay, so d solve the coupled, sorry, so coupled equation is x t equal to minus 0.5 x t plus y t comma y dash t minus equal to minus x t minus 0.5 y t. So this is the coupled equation, where basically coupled equation means that there are one independent variable and two dependent variable, and the differential equation has both of the dependent variable in one equation. Like this is the differential equation for x, but here at the right hand side you can see there is the x and also the y. As similarly for the differential equation of y dash t, which is equal to x minus xt minus 0.5 t yt. So this is known as the coupled equation, differential equation. 0, 1, y 0, 2. comma, we'll solve it for xt t comma t. So this is the solution for xt and yt. Now I will assign this value to some function xt t solve y yt to. So we assigned this xt and yt to two different function, that is capital X of t and capital Y of t. I will do the parametric plot. X t yt comma t equal to oh, capital X, this will be capital Y. So this is the parametric plot where the x-axis denotes the value of capital xt and the y-axis denotes the value of capital yt. Okay, so now I will write the code for the Euler method which has been shown in the lecture, but I will use different example that I have shown in the last class, where I have used the Euler method to solve problems numerical. But now here I will do that with the mathematical code. So f of equal to minus y yi equal to 1 xi equal to 0 xf equal to 1 n max equal to 100 h equal to xa minus xi by n max n. So this is the initialization. Now this is the for loop. Set 1 to xi yi plus xi y. Something is wrong. Okay, data set 1 x. Oh, So now this is the first problem I have solved numerically by hand, and then there I have shown calculated the value up to 1. So the problem is that y dash equal to minus y, and the initial condition is y0 equal to equal to 1. So xi equal to 0, yi equal to 1. So then I have took h equal to 0.01. So now here the h is xf equal to 1, xi equal to 0. So 1 minus 1, which is 1 by 100, that is 0.0.01, and calculated the value of y at 0.04. So if you recall, then you can see that we had obtained that the value of y at 0 is 1. Then we have followed this value up to this point. Y at x equal to 0.04 is 0.960596. So this is the whole table up to 1. Okay. So now again we can use some other example to get the solution. Like if we replace this particular differential equation with y minus x, sorry, so here the initial value is y equal to 2 at x equal to 0. Here you can see this is the data table for this one. Now what we can do is we can plot data p is data set 1, so this is the plot for the data table. Now again we can change this particular value y, and now the initial value I will change y equal to 0 at x equal to 0. Okay, so okay. No, this one is not working for here. No. So it gets just a different value. 3x plus y by 2. with the initial condition y equal to 1 at x equal to 0. So this is the solution. Now what we can do is we can increase the function n max. So now let's do this 50. Replace this with dataset 2. Data p2. Okay. Now again I will change this to 100, and then I will change this to set 3, 3, then I will plot the dataset 3 as data p3 dataset. So now these are the three solution where I have changed the maximum in max, that is 10, 50, 100. So basically I have reduced the value of h every time. Now I will just show three of them. Data p, data p2, data p3. So here you can see that this the plot with the large spacing, that is the corresponds to the n max equal to 10. So basically these two plots are correspond to the 50 and 100 points. So you can see that the plot corresponds to the 10 points is actually coming a little lower, but this 50 and 100 is almost uh, coinciding with each other. So this is the thing I have shown there, that when we use Euler, we have to go to the very low value of h, so we can get the greatest accuracy, or the solution will converge to the exact solution. Okay, so now I have shown already a lot of integrate. So now I will go to a little complex thing of integrate. So here I will define a function, that is y three y cube minus exponential of sine of x comma 7x square plus square root of y power 4 plus 1. So here I have defined a function v of xy that is basically represents a vector field 3y cube minus exponential e to the power sin x and 7 plus 7x square plus square root of y to the power 4 plus 1. So so to visualize the vector field, vector plot v x y x minus 3 3. Do anyone have any question? Hello. Okay, so vxy x from minus 3 to 3 y minus 3 to 3 So this is the vector plot of this particular function. So here you can see that the flow is in like this direction. So basically the problem is here that uh, use Green's theorem to compute the integration of uh, basically line integral of 3y minus exponential of sin x and sin x dx plus 7x plus square root of y to the power 4 plus 1 dy. So this is the problem. So basically this particular part will be integrated with respect to x, and this particular part will be integrated with respect to dy. So basically if you want to see the Green's theorem, so Green's theorem is like this one. So this is what I am saying, that there is a part that is the integral of L dx, and then there is a part that is m dy. So if we want to calculate this integral, we have to do a double integral of del m by del x minus del L by del y. This is the Green's theorem. So basically to get this form, we have to take the curl. Curl of x, y with respect to x1. This is the curl of the vector field, so we'll get 14x minus 9y square. Now integrate C x square root of 9 minus y whole square plus square root of 9 minus y y minus 3 Okay, so I think I have to use the mathematical desktop. Integrate yes. Okay, so this is the curl of the vxy. So basically curl gives us this part, then we have to integrate over the dx and dy, so there will be two integration. So the two integration is done in two steps, that is integrate x minus square root of 9 minus y square, square root 9 minus y square, so we'll get this one, and then after that we have integrated this with respect to y, that is the limit minus 3 to 3, we'll get 7 to 9 pi by 4. So basically we are doing the integration inside this circle, so then we get this 7 to 9 pi by 4. So this is the application of the Green's theorem, so where we just avoided that line integral because it will be difficult to do that, so we change the method mode of the integral from line integral to a double integration, which is known as the surface integration, and then we took the curl of the vector field and then integrate with respect to x and then with respect to y. So do you guys know about the Green's theorem? I mean, I just used the example, so I'm just asking. This was one of the good example of double integration, so I just used the Green's theorem. Okay, so you guys don't know about the Green's theorem. Okay, so then I will talk about Green's theorem in the next class, because that will do some some calculation to. So I have to show some calculation regarding the Green's theorem. So I'll do that in the next class. Now what I will do, I will show another mathematical code where I will show a motion of hello, am I audible? Okay, so this is a problem of a mass that is on a conveyor belt, and it is connected to a spring with the wall. So the velocity of the belt is Vb. The spring has a the motion of the spring is KL minus x, and the friction is minus a v minus belt Vt. Okay, so now the equation of motion is, mx double dot t equal to spring Fs, which is working in this left direction, and then the Ff, that is working in the opposite direction. So spring xt plus friction x dash t. So this gives the equation of motion with at t equal to 0, the spring is uncompressed, so x0 equal to L, and the velocity is 0, so x double dash 0 is 0. Now we have to solve this equation. So I'll just enter the line because I have already written it. So solution is equal to d solve cis x. Cis is actually this whole equation. So d solve cis xt. So this is the solution. This is a big solution which I. So now I have suppressed the solution using the semicolon. Now what I am going to do is I am going to write the position and the velocity with the function of m, k, a, v, b, t, these 5 variables. So position and velocity equal to xt and x dash t. So xt is the displacement, so which is position, and x dash t is the velocity with using this solution. And now using full simplify, we get this two solution. First one is the position and the second one is the velocity. Now we can do the parametric plot. Okay, no, that parametric plot will not work anymore. So now we will use the manipulate to see how the position and velocity works. So the first is so here four things are four parameters we can control: mass of block, spring constant, belt velocity, and friction coefficient. Now okay, so if we use this thing, so we can see the oscillation in the position, velocity, velocity. Yeah, so the position is shown by this blue line, and the velocity, the yellow line, is Vb, which is the constant velocity of the conveyor belt, and this is the velocity of the mass or the block. So now if I increase the mass, you can see the change in the nature of the equation. So the oscillation is decreasing. Now I am increasing the spin constant. You can see the oscillation is increasing with the spin constant. Now I am increasing the belt velocity. So you can see the yellow line has goes to 6 from 1, and here the amplitude is little increased. Now I am increasing the friction coefficient. So as you can see, with the increase in the friction coefficient, so with change in the belt velocity, you can see the velocity peak, this is changing. So now it is at 4 around, and here you can see that this is going to 5.5. Now the friction coefficient, when we decreasing the friction coefficient, it is showing some kind of oscillatory motion, but when we are increasing the friction, it is showing damping oscillation. So basically the friction is working against the oscillation, so it is actually gives us the damping force. That's why at with increasing the time, the mass is going at rest with a certain position. Here it is 2, and the velocity is going to 0. So with increasing the spin constant, actually we get back the oscillatory motion, but the friction coefficient is actually acts as the damping force. So we can see that from this particular these two plots. So this is a way to actually formulate a complicated problem in Mathematica. So we write the force acting or force with separately. Like for belt, the velocity of belt is Vb, thus force on due to the spring is K minus L minus X, K multiplied by L minus X, then the frictional force minus A V minus belt Vt. Then we write the differential equation m x double dash t equal to spring xt plus friction x dash t, as the friction is a damping force, so it will be proportional to or a function of velocity. So that's why it is written as friction as a function of x dash t. Then there is the initial value of displacement or the position of the block, that is equal to L. sorry, the initial position of the mass. So it is the displacement is up to this point. You can see in this gray picture, that is the unstressed or uncompressed string, that is here it is shown in the gray line, which is actually beneath the main diagram. So the block is at this particular position when t equal to 0 and x dash 0 equal to 0. So the velocity here is actually 0. Now we solve this uh, differential equation with DSolve. Then we assign the solution to position and velocity function using this line, and then we get this complicated function for position and velocity. Then we actually use this manipulate to see the effect of position velocity with having the controlling parameter mass of the block, spin constant, real velocity, and friction coefficient. Now again there is a circuit, LCR circuit. So this is the L, this is the R, and this is the C. So here we are going to get the voltage. So now there are 3 points, that is okay, so these subscripts have somehow it's not working. So these 3 points we are measuring the voltage V3, V1, V2, V3, I think. Now the first line is denoting the cleared all RLC. So if in any previous instance we have assigned value to R, L, and C, that value will be erased using this particular line. Then the voltage so VR equal of T is RI LT, and then VLT is V1T minus VRT minus VCT. So the system of equation is LIL dash T VLT and CVC dash T ILT. So these two are the differential equation we get from the LCR circuit. So now again this is the initial condition IC equal to IL at 0 equal to 0 and Vc at 0 equal to 0. So basically the voltage at the capacitor is 0 and current through this inductor is 0 at t equal to 0. So now using these equations we are solving the differential equation. Okay, so this I have executed the command of this line. Now I will do the same thing what I have done in this step. After solving the equation, I have assigned the position and velocity from this particular solution. So I will do the same thing here. Now I will use the manipulate. So here you can see so basically what we are going have done in this problem, we have actually found out the voltage of this capacitor and the current that is flowing through this inductor. So that is denoted by VCT and ILT. So now we'll just there are 3 controlling parameters, that is this R, L, and C. So R is the resistance of this thing, L is the inductor, and C is the capacitor. And now So with changing the R, you can see the change in the nature of the VC and IL. So by changing the L, you can see the oscillation is decreasing. So in this way we can change the RLC, the value of RLC, and we can actually see the effect of these parameters on the solution of LCR circuit. Okay, so I have a question. If I provide this file as a PDF, that will that be a help of any help? Hello. Okay. So so these codes are fine, right? I mean, you can understand this code. What I am feeling that these codes are a little bit complicated and tricky. So can you understand this code properly, or do I need to explain it more detail in the next class? Uh, Arif, is it possible to speak, or is there any problem? I mean, yeah, I can do this in the chat box also. Oh, okay. So you are speaking, but I cannot hear any voice from your side. So anyway, okay. So I will upload this as a PDF file, but let me explain this little more thoroughly. So basically, the point of teaching the simple harmonic motion and all those damped and forced oscillator problem is that uh, those problems can be used in this particular problem, this kind of specific problem. So all of these are actually solving the differential equation or solving the harmonic oscillator problem. So here this mass is actually exhibiting a oscillation, but what different is that the mass is actually oscillating because of this particular conveyor belt. So the conveyor belt is rotating and moving trying to move the mass in the right direction, and the spring is uh, actually pulling the mass to the left direction. So these two forces, Fs and F small s and F, these two forces are opposing force that is trying to balance the mass on the conveyor belt. So that's why it is happening that this mass is actually exhibiting the oscillation. So now in form order to formulate the problem, we have written this particular equation belt v of t as Vb. So this is the conveyor belt has a constant velocity, that is Vb. Then the spring has a force executing a force, that is k l minus x. So k is the spring constant of this spring, then the compression or the displacement of the spring is l minus x. Then the friction that is actually acting here, that is actually acts as the damping force, so it is written as minus a, so minus a v minus belt vbt. Now these three things actually construct the equation of motion for this particular mass, which is written as this mx double dash t, which is the force, total force acting on the mass, then the spring that is working in the left direction, and the friction that is working in the right direction. Now this is the differential equation, where in the previous classes I have mentioned only simple harmonic motion, that is x double dash is equal to minus x or something like that, but here this is a more complicated because there are a lot of things acting on the acting on this mass. So now this is the differential equation, then this is the initial condition x0 equal to L, then this is another initial condition x double dash equal to double dash x dash 0 equal to x. So we are solving a second order differential equation, so we need two initial condition to properly solve the system, so properly solve the ODE. So this is the initial condition for displacement and this is the initial condition for the velocity. So the initial condition for displacement at t equal to 0, the spring was at L, sorry, the mass was at L, so the length of the spring was L, which is from here to here, and the mass was here. Now at that point of time the velocity was 0. So this is the whole problem. So this is the whole differential equation with the initial value. Now we use the dissolve. Then using the dissolve we solve this differential equation and assign the solution to two functions. One is position and another is velocity. These two functions are depending on the variables m, k, a, vb, t. So m is the mass, k is the spring constant, a is the acceleration, vb is the velocity of the no, a is the damping factor, vb is the velocity of the belt, and t is the time. So these two things have been, so after solving we get these two things, position and velocity. Now this position has this complicated form, and then this is the velocity. Oh, okay. So L was assigned a previous value, so that's why it was not working now. So here you can see this is the actual solution of the function xt. So this is the form of xt. Now after using full simplify, we get xt as this and x dash t, which is velocity, as this. So these two are assigned to this pos function and vel function. Now after that we are using that manipulate to see the effect of mass of the block, spring constant, bell velocity, friction coefficient. So here we have plotted the position with time t from 0 to 2 and velocity with the range of time from 0 to 2. Then we get these two plot where we can manipulate or control the mass of the block, spring constant, bell velocity, and friction coefficient. So here you can see the mass of the block is actually reducing the oscillation. So what we can do is we can actually increase this range. Now you can see that mass of the block when you increasing the mass of the block, the oscillation is continuing for a longer time. Now I am increasing the spring constant. You can see it is increasing the oscillation, but it is not happening for a longer time, but it is increasing the oscillation. Then so basically the spring constant in using to oscillate the block the mass very quickly. Then the increasing the belt velocity, is affecting, like it is actually increasing the velocity. So this yellow line is goes up to 10, and so this one increases to 4. Now when the belt velocity is 1, this particular thing is going up to only 0.4. Then the friction coefficient. So when the friction coefficient is increasing, okay. So this A is the friction coefficient. I was saying this one is the damping constant, but it is actually friction coefficient. So what is happening, that when I am increasing the friction coefficient, the mass is coming to a rest. It is not oscillating. Now I am changing the mass of the block. Now increasing the mass of the block and friction coefficient, you can see there is a little oscillation happening in the motion. So this is how we can see the effect of these 4 parameters. So this is the actual visualization of a physics problem in Mathematica. So have you come across any kind of this problem? Okay, so you are facing problem in coding Euler and RK methods. Okay. So the RK Euler method is discussed in the lecture, I think. Okay, so specific linking function. So I could not understand what is the exact problem. I mean, what function you are talking about? Initializing a function and calling it for different differential equation. Okay, so are you talking about this part? And so basically here I am using a function and then calling this function at here. So are you talking about this part? Oh, okay, I got that. So basically you are talking about the making a module, right? Okay, okay. Yeah, actually I was supposed to include module in the next problem solving session. Okay, okay. So I will do that in the next problem solving session. So two things I will include in the next problem session. One is the Green's theorem and another is this module. So in the next problem solving session, I will show how to construct module for Euler, modified Euler and Ranjit-Gupta method. Okay. So with that, I end today's class. Do you have any other question, Arif? Okay. Thank you very much, Arif.